Hello and welcome to this low-level JavaScript series where we're attempting to build what I think is the world's first RISC-V CPU on an FPGA. This is episode 6 and we've been making some really good progress in the last few episodes, and actually I'm really excited about today because I think if all goes well then we're going to be able to do something really cool by the end. So let's just take a little look at the sort of the program here, the program of things to come. I mean, if this is your first time tuning in, by the way, exactly what I said in the beginning, trying to build a RISC-V CPU on an FPGA. Super as simple as possible, but yeah, it's a processor, so there's some complexity involved, and I'm not actually beginning right now with the actual hardware, with the HDL. Instead, right now I'm building an emulator, and I'm building a really low level emulator, as in I'm trying to actually just model the hardware as low level as possible, so that I can just work out all the hard stuff, work out all the signals that are going to move through the pipeline stages and all of that kind of stuff, so that when we get to the actual FPGA stuff, it's more about translating what we've already written in the emulator and less about and that will allow us to focus on the difficulty of the FPGA itself and all the difficulties that come with that, rather than trying to do everything at the same time. So today we're going to tackle jumps. That's the idea. We're talking about unconditional jumps here. So we're not talking about branches, which is a related but slightly different thing. We're talking about jumps. So this is like function calls. This is like goto. And what you'll find actually is that the way RISC-V works is that it actually handles all of these like in 1 or 2 instructions, and it's really cool. So follow-up business. The first bit of follow-up I have is that in preparation for this episode, and just like when I was thinking about how I'm going to tackle it, I realized that I just wanted a couple of utilities, and I ended up just prototyping them out just to make sure they did what I did, because it ends up being actually a little bit trickier than you can really trick yourself out on this kind of bit manipulation stuff if you're not thinking too hard about it. So I've written 2 utilities. I can show you them right now. Slice32 and bit. And the idea with that, and let me just zip over to the spec here, and let's just go to a page with like the jump instructions, since we're going to implement those. We've been seeing a lot of diagrams like this that show us the bits of an instruction and then what the different parts constitute. And so when I'm talking about a slice here, what I'm saying is like, hey, I want to grab this section, right, which is here. This is immediate bits 19 down to 12. I want to grab this, and that goes in the instruction from 19 down to 12. So what I would pass to slice 32 is these indices 19, 12. I would pass the instruction itself, and there's actually an additional parameter that I've put there for convenience sake, and that is like a shift parameter or a position parameter. And what it allows you to do is to, like, if we just use it and we didn't provide that optional parameter, if we just got this slice, we'd actually isolate this part, and we would have it we would just take this part of the number and have it. So not this number and then with loads of zeros after it, but like this number shifted down, nothing else above it, just that little slice that we're looking for. And then the shift allows us to like basically reposition that anywhere we want, so that we can actually reconstruct numbers, because as you can maybe see, or maybe haven't had a look here, like we have one immediate value and the bits are all kind of messed up here. So they're kind of in a different order, and we need to reorder them. And so when we're taking slices, we can actually immediately put them in the right positions. So that's that. And then bit is much simpler. It's kind of the same thing, but basically it also takes an index and a value, and basically isolates that bit at the index that we talk about, and optionally shifts it into position. So that's how that works. It's the only bit of coding I've done in between now and the previous episode where we did loads, I believe. And so the next piece of follow-up, and I'm going to try to not focus too much on this now because we're going to come to it at the end, and I want to make sure that I'm not taking too much time today. But in the last episode, at the very end, when I was testing out load upper immediate, and I wanted to illustrate how you could combine load upper immediate with add immediate, and you could like construct any 32-bit value. That is indeed true. I kind of got confused by that because of the numbers that I chose, but it is true. But I was kind of like, oh, I don't understand how this works. And yeah, like what I've written here is basically what you do is you say, hey, compiler, can you please do this for me? You provide the compiler with the value, and it will work out how to make sure that that 32-bit is transformed in such a way between the two instructions such that you can load the value into memory. And to illustrate this, I'll just give you a really, really brief and quick illustration of this. There's a new folder inside the code. It's called system code. I'm going to rename this at some moment. And inside here is some C files. There's a little assembly file. There's a linker script, and there's some shell scripts. And basically, what we've got here is I've set up the RISC-V toolchain. I said that before, but in fact, I had not set it up quite correctly because it was targeting a more complicated version of RISC-V than what we're implementing here, since we are only implementing the integer 32-bit instruction set, and that was basically adding support for multiply, float, and double float, which is just what, that's like a standard processor, so that's what you expect. But for this is a much simpler processor. So I set up the toolchain, and I kind of did a little bit of research to work out how to kind of write some C, get it to compile without assuming that there was any kind of standard library or anything like that, and just figuring out the stuff that I would have to do in order to get it to actually make sure that the code compiled such that all the stuff was placed into the actual right addresses for this system. Like, we have a place where we say that the program ROM is, and we need to make sure that code that gets generated is generated there, and all the relative addresses are like relative to that entry point. So I've done a bit of that. Kind of wrote this C file. If you don't know C, don't worry too much. We're going to go into this in a bit anyway. But basically, what we've got here is got this main function. It immediately calls this function called 42 with side effects. It's called 42 because it just returns 42, the constant. But there is a side effect that we end up writing to a raw value in memory. So we're writing to the RAM start, which is here, and we're writing this value. And obviously RISC-V instructions, they're 32 bits long, and they are only 32 bits long, at least in the ones we're implementing. And therefore, there's no way you can provide a 32-bit immediate. And in fact, if you look at the instruction set, there are like a couple of different kinds of immediate encoding. But for the most part, you can either load a 20-bit immediate or you can load a 12-bit immediate. And those get extended out, padded out, depending on which one you use. And kind of what you have to do is you have to use the load upper immediate to load something in the top half, and then you can use add immediate to just like add the lower part, and between those two you can get the full 32 bits. So kind of what you can think of here, and don't worry too much about this crazy thing that's going on up here. If you don't know C, like, I'm going to explain what this line is doing later, but basically this whole thing is writing to this address in memory, and we're going to look at the assembly for it in a second. What you have to keep in mind is it splits the number up. It's going to split the number up into two pieces. The first part is going to be the upper immediate. That's basically this part, and then it pads it out with zeros. So this would be our upper immediate, and then somehow we're going to get our, our kind of, I guess, our lower immediate, but it's just like, this is just what we add on. Like, this is our bottom part. And I've chosen this number, not for any particular reason, but because the 12-bit immediate that we specify down here, this gets sign extended to 32 bits before it's added. And since it has an F there, right, that means that there is a 1 in the sign bit. And that means that when this gets sign extended, it's not just going to be a simple add anymore. It's going to become a weird subtraction, actually. And it's not going to quite line up the way we want it to. So that was what I hit before. I'd accidentally put something with a sign bit in there, and so we didn't see the nice effect. If I had chosen a number that didn't have a sign bit there, it would have worked fine, which is funny. It's nice to bump into the edge case. It's not really the edge case, just like the second case. Okay, so what I want to do now is I want to show you the assembly that comes out of running this program. And we're only going to focus in on a couple of lines of it. We're going to go deeper into that later. So I'm going to switch over to the terminal here. And I've got two windows. We'll just look at one of them for now. I'm in this directory with my stuff, and here this main file, that is an elf file that contains the you know, all the executable information, but it's got like all the assembly in there. So we can disassemble that. I'm going to use my RISC-V toolchain for that. I'm going to use a program called object dump. We're going to use its disassembly function, and we're going to do it on the main. So that's going to give us this this RISC-V code. And what we really want to look at is just something inside. You can see we have actually got our function names here. So we've got main, we've got something called _start, which we'll talk about later. And then we've got our 42 with side effects. And so the first few instructions here are just dealing with the stack. So those first 3 instructions, all they're doing is like setting up the stack. When you enter into a function, like that's what the compiler does. It like makes sure that the stack stuff is there and done. And it does the inverse at the end of the function. So the next couple of lines, this is actually what are, like this is what that one line of C was doing when we did write to RAM start this thing. So it's these lines. So the first thing it does is it loads an upper immediate into a register A5. We're going to talk about these register names later because they don't quite correspond with kind of what we've been seeing so far. We load a register into A5, and what you can see that we're loading there into the upper immediate is the address, right? The RAM start address. And we don't have to do anything more to it because it's going to 0 pad the last 12 bits, and that is indeed the address that we want to write to. So then this next part is the combination of the load upper immediate for the immediate value and then the add immediate afterwards that's going to make it right. So how does this work exactly? So what you see is that we're loading into a different register and we're loading kind of the beginning here. But what you can see is the compiler has done a little trick, and what our number was, and I'll go back and show you, and I'll maybe copy it into the terminal here just on the side. So our number is just this, and so the first set of numbers here, you can see that it's actually a 0 on the end, but RISC-V is going to put a 1 there. So it's going to be a 1, and then it's going to get 0 padded at the end with 3 zeros. So it's loaded kind of a different upper immediate into that place. And then you can see that it adds minus 256. Now, minus 256 in this case, like it's representing this 12-bit immediate value that we have, and in the 12-bit case, this is going to end up being our F00. That is F00. And so what ends up happening is when you add these together, and minus 256, obviously you have to think about that then being sign extended to 32 bits. So there's going to be tons of 1s in the upper 20 bits, and then there's going to be like the rest of the number that we specified. And when we add that extended number to this sign extended number, we're going to get a new result. It's going to overflow because it's going to be basically two really big numbers being added together. We ignore like the stuff that overflowed on the top, and what comes out is the actual correct answer, which is this. And yeah, I could run you through the math, but I actually think it's more fun if you pause the video now, just like open up, you know, Node or some other environment where you can create these kind of numbers and just do the operations, do the shifts around and everything, and convince yourself that this works, because yeah, it's pretty cool to see. Anyway, so we're going to come back to the C stuff at the end, but for now let's actually move on. So today we're going to implement these two instructions, right? These two instructions, and they are going to give us access to actually quite a lot of different behavior. There's a lot packed into these two instructions, as it were. And the two instructions are JAL and JALR. So jump and link, and jump and link register. And yeah, now it's probably a decent time to zip over to the spec and take a look. So we're in the control transfer instructions section. So there's a little bit of text that just talks here about the fact that there are two different kinds. We have unconditional jumps, that's what we're dealing with today, and then we have conditional branches, and those we're going to deal with next time. Control transfer instructions in RV32i do not have architecturally visible delay slots. Yeah, I don't think it's even worth us talking about delay slots, because we're like, you know, this is built for people who have built, like, who are involved in the RISC architecture stuff. But if you're familiar with other RISC architectures, for instance MIPS, they have something called delay slots, and delay slots are something that they kind of simplify the process of pipelining, and they basically shift some of the work to like the compiler when it's generating code. And what RISC-V is saying is we don't do that. That's not a thing we're doing here. So yeah, and the interesting thing is they say architecturally visible, which means that you could implement it in your processor, but you don't expose the details of it. It's pretty interesting. It's interesting to get into like hardware stuff, like especially as a software person, and realize, I think maybe I've mentioned this before, but I find it so funny that, you know, before you really start getting into this stuff, you imagine that like hardware is hardware and assembly language like represents what's happening on the chip. And, you know, in our case, it probably is going to for the most part. But in complex processors, the assembly language is absolutely not what's happening really inside the chip. It's a really interesting thing. Like, it ends up being translated into some other system. It's really yeah, you can think of it even being an interpreted language on the, like, the interpreter is this, yeah, anyway, it's completely not the point for now. Anyway, so we're going to look at unconditional jumps. The jump and link instruction uses the J-type format, where the J immediate encodes a signed offset in multiples of 2 bytes. That's it. That is actually important, and we'll see what that means in a second. The offset is sign extended, like everything, and added to the PC to form the jump target address. Jumps can therefore target a plus or minus 1 megabyte range, 1 MB. I can say it just feels so wrong to say MB. JAL stores the address of the instruction following the jump, which is PC plus 4, into register RD. The standard software calling convention uses X1 as the return address register and X5 as an alternate link register. And yeah, so that's another kind of interesting part that we're going to get into later, and that is the idea of this calling convention. And more specifically, we're going to have a little chat about the wider concept of the ABI and what the ABI means in terms of the processor, in terms of the compiler, in terms of like all of these things working together. And it's going to be pretty cool. Okay, so plain unconditional jumps, which is the assembler sudo op j. Sudo operations is also something we're going to talk about, are encoded as JAL with RD equals X0. So basically not storing the return address. So J the J instruction is just go to. Like, you're not returning from that, like, at least not in the sort of like stack sense, right? You're not like coming back. Okay, so what we have is a relatively straightforward instruction. We have 20 bits dedicated to an immediate, and you can see this is different from a lot of the other immediates that we've looked at, but you can see that, like, if we look at this immediate value, you can see it's specified as 11 down to 0, right? So it's telling us that we've got a 12-bit number, and it goes from like bit index 0 to bit index 11. And this is different to up here because this is telling us we've got a 20-bit number. Well, in fact, it's telling us something kind of different. It's sort of implied, but it doesn't go down to 0, notice. It doesn't go 19 down to 0 like you might expect a 20-bit to be done. Instead, it goes from 20 down to 1. And that is because of this, the fact that it says that it encodes signed offset in multiples of 2 bytes. So the idea here is that there is an implied 0 on the end. And like, we need to put that in place. We need to make a 0 here before we do the sign extend, because there's no reason for this to point to an unaligned address, if that makes sense. There's no, like, in fact, this allows us to write 16-bit aligned addresses, I believe. But the point is, it doesn't allow you to just do arbitrarily aligned addresses. It's only encoding, like, kind of what we might consider to be properly aligned addresses. And so, yeah, that's pretty interesting and something that we need to keep our eyes open for. The other part of this whole thing is just like, and I still don't know really why this is, and maybe someone can tell me. But the immediate is not just encoded as 20 bits, like the kind of in order. For some reason, those bits get kind of split up into different places. So we have bit 20 here. Then for some reason we have like what should be bits down 10 down to 1. Then we have bit 11. Then we have bits 19 down to 12. So what we're going to have to do is we're going to have to kind of unstitch these and put them in the right position. And maybe now, seeing this, you can have a really good idea about why I implemented these slice and bit functions. So to kind of take that theory that we just looked at and think about how we're actually going to attack this problem, we're going to compute the address in the decode stage. That's going to involve us decoding this immediate. It's going to involve us adding to the program counter. And then we're going to write the program counter back to the instruction fetch stage, because the instruction fetch stage owns the program counter. Excuse me. And that might be something that changes around a bit. I'm not exactly sure, but like that, maybe it won't own the program counter at some point and it will be outside, and actually we'll write to that in a different way. But for now, I'm just going to do it this way. And then later we're going to write the address that we're linking, the kind of return address. We're going to be writing that back at in the rightback stage. So we've got most of the stuff in place for this. We are going to need to do a bit of modification here, because right now, like, the instruction fetch stage does not expose the program counter or PC+4. And we also need to make it, like, we need to figure out a way to get the instruction fetch stage, like, to be able to modify the PC, because right now that is also not possible. So there's some of the problems we have to tackle. Let's just get straight into it. Let's start in the decode stage, because the decode stage, yeah, it's kind of, most of this is going to be relatively straightforward, I think. So we're going to have, coming out of here, I'm going to make a couple of new registers. One of them is going to obviously be like, is this a JAL? Like, is this a jump? And I'm going to separate the idea of the, maybe I don't need to do this, but I'm going to separate if this is a JAL or if this is a JALR. Don't know if that's strictly necessary. The other thing is we're going to compute something that I'm going to call the branch address. We're not really branching as such, like we're more like calling into something with this because they're unconditional jumps. but I'm going to call it the branch address anyway, because probably this is just going to get shared. Like, we'll work out what this address is going to be based on, like, if it's a branch, if it's a jump, whatever. So we've got these two new registers that I'm introducing, and we're going to need a new immediate. And yeah, so if we look here and we go to 104, we'll see that we need to implement this J-type immediate. And yeah, although I think it's going to be easier to look at on the other page, so I will stay on that one. Where is it? Control transfer. Oh, it's on page 16. Yeah, this is yeah, hopefully this doesn't get too confusing for me. It is a bit later in the evening, and I am a little bit tired, so hope I won't get like too jammed up on this. Alright, so the first part's easy. In the first part, we're going to be grabbing like what is bit 20, and that's just at bit 31. So I'm going to use this bit function that I have. And actually, quickly before I do this, I'm going to make a little variable here called I that's going to be the instruction next value, because yeah, like this is going to get probably kind of long, and we use this value quite a bit. Probably be like fairly relevant to do that a bit further up, but maybe we'll move that later. Okay, so what do we need? We need bit 31 of I, and then we can push this into a position, and the position I'm going to push it to is 20, right? Because that is the position that it needs to be in according to the spec. And then we are going to be next, we need to, like, we're reordering this, right? So we're not going to do it like one by one. We're going to get this part now. So we're going to take this, and we're going to be putting it up here at position 19. So we're going to take, coincidentally, maybe not coincidentally, I'm not sure, but coincidentally we're going to take 19 down to 12. And notice that I'm ORing these together, right? Like, so, like I'm taking this bit, I'm shifting it up, and then I'm going to OR in more. So we're like slowly constructing this address as we go. I'm going to use the slice 32 function. We're going from 19 down to 12 on the instruction, and we want to shift it up to 19. So, okay, I think that is the way it should work. Next, now we need bit 11. That's at bit 20. So here we're going to come in with a bit. Its index is 11. No, index is 20 of the instruction, and then we're pushing it to bit 11. Then, finally, we're going to take bit 30 down to 21 and shift it up to bit 10. Okay, so what did I say? 30 down to 11. Is that correct? 30 down to 11? I'm losing this already. 21, of course it's not to 11. It's way too much. 21, the index, and like I said, we're pushing it to 10. That gives us, if I haven't messed that up, that's going to give us the immediate. And what I might quickly do, because I'm, you know, I am a little bit averse to making a mistake here. Yeah. What I'm going to do is I'm going to take these instructions. I can't use the export, so let's get rid of that. I'm going to dump these into the execution environment, and then I'm going to create an instruction. Yeah, what I want to do here is I want to construct a value that's going to kind of make some sense. What's going to be the easiest way of doing this? I think doing something like we'll have a 1 and then a 0 and then a 1 1. and then a 0, 0, and then a 1, 1, 1, and then 0, 0, 0. How many bits do I have so far? 12. Whoop. And then 1, 1, 1, 1. That should give us 16. 1, 0, 0, 0. And then that should be our full 20-bit immediate. So that's kind of like that's how it's going to be encoded, and then kind of like if we translate this to how it should look when it comes out, well, it's going to be 1 in the top. How's it going to work? Just checking in. So we have 1, 10, 1, 8. Yeah. 1, and then we need 10 bits, then 1 bit, and that should be 8 bits. Yeah. So we have that 1. Then we are going to take the stuff that goes from 19 down to 12. So that's these 8 bits on the end. Then we're going to have this this bit, and then these ones. So this is what we expect to come out of the immediate. I hope this is making sense to some degree. And then for the rest of the encoding, we've got the 5-bit register and the 7-bit opcode. So how should we do that? 1, 2, 3, 4, 5, and then just like 1, 2, 3, 4, 5, 6, 7, something like that. That's going to be like our quote-unquote instruction. So let's just say const I equals. I'm going to paste this in. I'm really hoping this all just works first time. And then we're going to compute this J immediate, and then we should be able to see if it's the same. Oh, that's yeah, just need the word let there. Okay, so J immediate, toString 2. All right, let's take a look at that and let's see if that matches. Oh, controlled seed in the terminal. That's obviously not a real. Oh, good, brilliant. Yeah, those match. You can see that it like highlights the match for us. So, very pleased with that. That was just a safety check for me. Okay, but that's not the end, because we need to shift the whole thing up by 1. So let's take that and shift it by 1. And then we need to sign extend this. So luckily we've already got code for that. Sign extend 32. Question. And the number of bits we're providing here is now 21, right? It's not 20 anymore, it's 21. And then everything else is our argument. So yeah, that should be our sign extended 21-bit immediate. That's going to act as our offset. So else if this dot is JAL dot next value, then in that case this dot immediate 32 dot value is going to be J immediate. I don't really know if we need to store it, but I'm going to do it. And then we can compute this branch address. So the branch address is going to be, well, this is the point which we now need the program counter, right? And we don't have that yet. So let's actually, now let's actually zip off to the instruction fetch, which is a stage we haven't touched, and unfortunately doesn't have the conventions that I've set up for the other stages yet, which is that like this is like get instruction values out. See, we were returning one value, and I switched to a convention where we return an object with values, and now we need multiple values, so that would have helped. All right, I'm going to rename this symbol to be get instruction values out. and we will no longer return one value. We'll return an object. Okay, so it's going to be broken, but I'm okay with that for now. So I think we're going to need two registers. We're going to have two program counter registers. We're going to have PC and we're going to have PC plus 4. And kind of, you can see we're kind of doing that right now. We're just like, we're just always incrementing the PC after we've fetched the instruction, which is fine. But what we actually want to do is like sort of, I guess, when we enter the thing, we can think of it like, we can think of ourselves like writing the PC value as PC plus 4 value. This won't quite work like this in hardware because we would expect that this takes one cycle, so it's not quite going to work exactly like this. Well, in some ways it actually will, but don't worry too much. So we're loading up the PC, and we'll just immediately say this.pc plus 4 the value is going to be the PC next value plus 4. That's simple enough. And then we'll want to use that next value instead. We need to latch PC plus 4. So we want to pass on the PC, and we'll want to pass on PC plus 4. Alright, so that's good, but some stuff's going to be broken from that. Like in Decode, yeah, you can see actually we're going to have the wrong kind of interface here. So we're going to now call this GetInstruction values in, and we're not going to return a number anymore because that was just the instruction. Instead, what we're going to return is the return type of the instruction fetch stage, and specifically from the instruction fetch stage, the get instruction values out. Like whatever that returns is what we're going to have in this thing. And we could also, I guess, just say this whole function is what comes out of instruction fetch, but this, to me, this is now communicating the idea that we have some function which has given us the same type, which is returned by instruction fetch. And actually, I spoke to someone today in a comment on YouTube about this pattern in general, and they, I mean, fairly rightly actually, in some ways, said that kind of the whole idea of using return type is maybe a bit, it maybe doesn't communicate intention. Personally, I think it does communicate the intention, because like the values that come out of the instruction stage, like that is specifically, like that is the type that comes out of this. Like this method produces the values that come out, so it is the type. What might be a better pattern, and I don't think I'm going to do it now, but what might be a better pattern, you know, to go in and do with all the stages, maybe I'll do it off camera, is to just actually create a type for this in each pipeline stage and export that instead, and then use that type. For now, this works. This pattern is used everywhere else. I'm not going to change everything right now, but this allows us to get those in. What that does mean is, we need to also, we need to latch and stuff, that kind of stuff here. So yes, we have this idea of get instruction in. We want to actually call this get instruction values in, which is like this. So that's now okay. That all lines up, but still when we do this, that's now wrong, because we want to actually get the we want to get things out of this method. Let's put a little new line between those. And we'll end up pulling out the PC here. And we're going to end up passing the PC and the PC plus 4. We're going to pass those forward because we're going to need both of those. So the branch address value, after all that, turns out to be PC plus J immediate. It's always plus J immediate. And so you see that we're going to compute this. Is it always plus J immediate? That's actually probably not going to be true. And we'll fix that when we get to that, which is probably going to be in this episode. But let's tackle one thing at a time. Let's, while we're here, just also make ourselves registers for these things, because we need to pass them forward. So let's also grab PC plus 4. Oh my gosh. Yes, alright. So PC, this.pc, value equals PC. This.pc plus 4, value equals PC plus 4. Excellent, all those things. Now, here's JL. We're going to latch that value. We're also going to latch the branch address. We're also going to latch PC, and we're also going to latch PC plus 4. And we're going to export, here's JL. We're going to export branch address. It's really, really annoying, sort of like, hey, here's the thing you're looking for, but also not what you're looking for at all. Okay. So that stage is sort of correctly fixed. This stage is looking all right. The one thing that's going to be wrong now is the index file, because the place where we actually like do the wiring between the stages is now going to be wrong. So decode, I think I changed the name correctly, right? Get instruction values in. Good. Okay, so get instruction values in is going to come from get instruction values out from the IF stage. So this is us passing these forward here. Yeah. Okay. And the one thing we actually need to do, like I said, is if this is a jump, and we already know it is in the decode stage, if this is an unconditional jump, then we already can set the instruction fetch to have the right address. And it kind of doesn't matter until we get proper pipelining. And when I say pipelining, again, if you've never watched this series and you're watching now, like, and you're confused by any of this pipeline stuff, it will kind of make sense to go and watch some of the previous episodes. But yeah, like when the pipeline becomes parallel, it's going to start making a difference, like when we sort of start sending values back through the pipeline, because it's going to cause us to perhaps invalidate stuff that might be in those earlier stages of the pipeline. And the further into the pipeline we are, the more stages we need to invalidate. Shouldn't be a problem. So what I want to do now is I want to go back to the instruction fetch stage and implement the possibility of this getting a branch address from somewhere. It's just, we're just going to have, yeah, let's just do this here. So we're going to have get branch address, which is going to be a function that returns a number. That's it. It's going to be a function that returns a number. And I guess we're going to have another function which is going to be called GetBranchAddress valid. And that basically between these two things, we're going to know like, hey, do we have an address that is valid? Yes, switch the program counter to that. And how should we think about doing that? Well, like we haven't implemented this yet. Oh yeah, we need to do this whole like song and dance of like doing this stuff. So now we're saying that we have those things, and then yeah, okay. So now we've got all of the got all the methods and everything we need. And what we can say is when we're assigning the program counter here, notice that we base our +4 on the program counter. Here we can actually say like if this.getBranchAddress is valid, like if we've got a valid address, use that address. And otherwise use like whatever the previous counter previous program counter was +4. I think that'll do it. That's going to do it for now. We might have to change things around in here once we get parallel pipeline, but that'll do it for now. This is now going to get a little bit more complicated because we're going to need to implement a couple of methods here. We're going to need GetBranchAddress, which basically what we're going to do is we're going to be looking to the decode stage, and we're going to be calling its methods. And you're going to notice, right, that at this point, this is going to be problematic because it doesn't. This is a TypeScript thing, right? Or I guess it probably happens in a lot of different languages. But what we're actually doing here is right now we're in the class definition. We're in the members and we're assigning members, and we happen to be initializing like a new class and everything. And so by using these lambda kind of functions, these arrow functions, they capture the surrounding context. So this is capturing the context of the class, and we're trying to look into this. And what you have to realize here is that by the time this is like being parsed, like by the time like TypeScript is kind of delving through the tree and like, oh, we're passing a class, blah, 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 blah. Oh, we're passing a definition, like for a class member. Oh, we're passing a class definition or class instantiation. We get all the way down to here. We know what this is, and we kind of know there is a DE member, but we can't tell its type or anything right now because it's not like pre-typed. We don't know the type until it's actually done this part of the work. I think this is going to be enough to fix that. Like we type it, and then hopefully at this, yeah, okay. So at this point it knows what this thing is. It's kind of janky in a way because like we're assigning all these things in the moment. Well, whether or not it's janky or not is up to you to decide actually, but we've now given the compiler enough information to know that this is valid, so it's okay to do. And it also, I prefer this over like saying the type of these things and then not initializing them, because there is then the idea that we don't know if we initialize them because we'd have to do it somewhere else in the constructor or something. In any case, we can call this get the coded values out, and then we can just look at the branch address. That'll do it. And to know if the branch address is valid, we can look at the isJL property, and we can say just convert that to a boolean. And now, wouldn't you know it, we've got our thing correctly done. And I think when we get the next address, we're also going to need to check that. So we might, we might want to expand this out a little bit. But anyway, this is the wiring. Okay, so at this point, we've got our instruction fetch set up so that we can actually replace the program counter. We've got decode coming in. decoding the fact that this is a JAL. Actually, we're not even looking if it's a JAL yet. That is incredible. That would have been such a weird bug because it would have had an initial value that would have been really weird to try and figure out. Okay, so the opcode for a JAL is this. And as you know by now, that we can't just paste that value because, you know, it's got some weird character after it. Didn't seem so bad there, but normally it inserts also like a new line. So that's the JAL opcode, and then based on if we have a JAL, then we're going to be writing the JA immediate. We're always going to be calculating the right branch address, so it's kind of tricky stuff here. But okay, so that all works fine. You know, maybe we should do this in this part. Like, if it's a JAL, we know we need to write the branch address. Otherwise, it can be 0 or whatever it was in the previous round. It doesn't really matter. Probably it should be 0, but yeah, we'll get to that. Okay, so at this point, we have indeed identified that it's a JAL. We've decoded its immediate value. We have assigned the immediate value and calculated the branch address. And well, probably we shouldn't do it like this. We're going to need to rearrange it a bit anyway, but there are some ways which we can make this work. Then we need to move to the execute stage. And we don't need to do anything in the execute stage as far as I know, but we just need to pass some stuff on, just like we've been doing in other places. So we need to pass on, is this a JAL? And we need to pass on, do you know, I actually think we don't need to pass on the branch address. Yeah, I actually think we don't even need to pass on the branch address because we're already sending it back. It's not a conditional branch at this point. We will need to pass it on because we're going to need to check branches later on, but well, for now, I guess we don't need to pass it on, so I'm not going to do it. Do we have values we need? We need to pass on the PC and the PC plus 4. Actually, we only need to pass on the PC plus 4. Because that's what we write into the return address register, as it were. So let's do that. What's the right place to put that? I don't know. I'm going to put it just below here. PC plus 4. So we're going to take that out of our decoded thing. So we get PC plus 4 out of that. Oh, actually, we're not really doing that pattern here. Oh, it's a little bit mishmash in some of these places. So PC plus 4. Alright, so we get those things, then we need to latch them. So we're going to latch, is this a JAL? We're going to latch the PC plus 4. Then we need to pass those forward. Oh, it's annoying. Okay, so execute stage I think is done. Then we get to memory access. Again, here we're not doing anything, although the memory access stage is, if I remember correctly, the memory access stage was the place where we end up like kind of defining the rightback value. I don't really know if this is the right place for that. It's probably not, but it's, for now, I'm just going to stick with it because otherwise, I don't know, I'm not going to mess around too much. So let's just get the things we need. We need isJAL and we need PC plus 4. We don't need to pass them forward anymore because at this point we simply need to say, hey, is this a JAL? And if it is, then this dot rightback value becomes PC plus 4. And then of course the rightback stage we don't need to do anything with because it's kind of already set up. No, that's not strictly true. I kind of want to collapse these things into like, do we have a rightback value, rather than doing it this way. So I think at this point I am going to do that. So instead of passing all of these things forward, we're just going to have private rightback value valid. Yeah, I think this is going to be a better way of doing it, which is going to mean we're not going to need to capture all these other things. We write them all to pass them on. I don't think we need them. So we don't need them here either. What we need is to say, like up front, we'll just say this dot rightback value valid value. Kind of a stupid name. But yeah, if it's a store, Well, actually, you know, this is really all we need to do. Like, the rightback value is valid if it's a store. So is store, and these are going to be 1-bit things, right? This is going to be either a 1 or a 0. So we can just OR them together, and if any of them are a 1, then it will be true, right? Just like we would do with logical OR. We can do a bitwise OR. So if it's a store, or if it's an ALU operation, or if it's a LUI, or if it's a JAL. Great, so we end up doing that. So we can get rid of all these, and the only thing we need to then say is rightback value valid dot latch next. And we're going to pass on rightback value cool, and then in rightback any of those end up being the case, then we write back. That makes it way simpler. I kind of like that a lot more. We'll end up simplifying this through the, and like what might happen is that like further back in the processor we'll actually have a value like this, and we'll move it forward, ORing it with more and more things as we compute further and further into the pipeline, and then that will probably clean things up a bit as we go back, but I'm not going to do all that now. So if I'm correct, and of course there can be bugs, if I'm correct, I think now we've implemented JAL. So we should go from beginning to end in all of this. So to do JALR, we've already decoded most stuff. We just basically need to calculate a new branch address for it. So yeah, so that's actually probably not too hard, right? To know if this is a JLR, ALR. I'm going to have to go and get the thing. We need to make a register for it. The value, let's grab its opcode, which probably only differs by 1 bit. Yep. And I've gotten rid of my thing, and I don't remember which bit specifically was changing there, so just copy it again. So that time we got a new line. Okay, so we don't need to decode the immediate because the JALR, as you can see here, JALR, it's just the immediate form, right? It's just the I type encoding. We've already done the decoding for that. I do just want to check back here in the spec to page 16. So the indirect, actually I didn't even talk about what this was, so I should probably do that. The indirect jump, which is jump and link register, uses the I-type format. And the idea here is that we use a register base address and then we use a 12-bit offset for that. So it's very, very much like the load and store instructions that we did in the last couple of episodes. Base register that has an address, 12-bit offset. And there is a trick here as well. So the target address is obtained by adding the 12-bit signed immediate register to register RS1, then setting the least significant bit of the result to 0. So what you'll notice here is that we don't have a 12-bit immediate that we shift forward by 1. We just have a 12-bit immediate and we just fix its last bit to be a 0. So no, like basically we're ignoring the last bit of this and we're just going to set it to 0. So that's fine. If register 0 is used, same story. Okay, this shouldn't be too difficult for us to implement. You can now notice again that if I bring this in and I paste that there, and then if we have a JALR, then our immediate is actually the I immediate, and the branch address is now. So in order for us to set this bit to a 0, there are a couple of ways we could do it. I think the simplest way is to... what is the simplest way? We could use this slice, which will allow us to slice, you know, the top 11 bits, and then we'll just shift them forward by 1. I think I'll probably do that. What we could also do is build we could build an inverse mask. So basically like have all the bits except maybe that kind of works better, but I find it a little bit of a tricky one. In order to build that mask, we can do it just for the sake of it. So it would be here we're going to have an I immediate, and then what we want to do is we just want, actually you know what, I'm gonna do the slice thing, because otherwise we're going to be dealing with like we actually have a 32-bit number, and when we invert the bits we're going to invert like the top 20 bits that we're not interested in. So we just do it like this. We want bits 11 down to 1 of the I immediate, and then we want to push it to we'll just do it. I'm just going to shift it up like manually instead of using the built-in shift, because I'm not exactly sure what position I should say this should go to. I think position 11, and then that would work. Oh, maybe I should do that. Yeah, I think that works. Trust in the code that I've already ran. Okay, alright. The only thing that we need to do now is actually pass forward the idea of the JALR. I'm just thinking, like, can we just fuse these two things into like one thing that just is jump? And I'm wondering if because that's all the next stages are going to care about. They don't care about if we got this from like the JAL or the JALR. We'll see about that. I'm not going to make too many assumptions. I'm just going to pass it forward, so won't take too much additional wrangling here. So we're pushing those forward in execute. So same thing. New register. Easy. Okay, memory access is JLR, and then at this point we just need to OR this in. This is kind of getting a bit unwieldy, so let's that's kind of I'm not sure how much better that is, but at least we can collapse it. Okay, so for the rest of this, no, there's one thing more. Yeah, you can see, right, that basically, since everywhere, the only place that we end up using this is like also ORing these two bits together, we probably only need for it to be is the one thing. I'll leave it like this for now. Okay, we're at testing. I believe we're at testing time. If all has gone to plan. Now, the reason I'm so excited about this, I just want to see like how long I've been going for, because I don't have a good sense of that right now. What's that? Just over an hour. Okay. I was really scared for a minute there that I wasn't recording. Okay, so you can kind of see that we've done those parts, and now we're into this part of the agenda, and that is the C program, the compiler, and the loading the 32-bit immediates. We actually already took a look at loading the 32-bit immediates, but now what we're going to do is, instead of hand constructing and encoding instructions, as we have been doing to test things in the past, and that works fine, that's basically handwriting assembly at like the bit level. Instead of doing that, let's actually use our C program, because at this point we can actually get that the compiler toolchain to build proper RISC-V binaries for us that are targeted to this specific architecture, which is RV32I, and using, well, I'll show you a little bit of it. This is not like my best work, and I've kind of copied all the code for the linker. I've kind of taken from somewhere else and just like, you know, jammed Frankenstein stuff around until I've got it to work the way I want, but I don't understand the linker script yet, and I need to understand it properly. It's not something that I've played too much around with. I've only ever done like small edits in linker scripts before. So anyway, we've got our C program. I promised that I would deconstruct this thing, and I will. What we also have, well, if you remember when we were looking at this breakdown, there was this additional function, and if you're astutely observant, you'll notice that this is actually like the very first address in the program ROM. And so like this is kind of our entry point code. This is like I've called it the bootloader, but it's not really a bootloader. It's literally 3 assembly instructions, and what it does is it sets up the stack. That's it. It basically comes in and makes sure the stack pointer registers are what they should be. So like in the LLJS VM, if you followed that series, you'll know that like kind of setting up of the stack and all of that kind of stuff, that was all sort of done inside the CPU itself. But that doesn't really make sense, because the CPU shouldn't really be super aware of like what the memory map is and like what like how much stack there is available. It probably should know something about how much stack there is, but it doesn't necessarily know all these details. And so actually what generally happens is a compiler is going to do like, it's going to insert this kind of information at the beginning of every program. And if you go and disassemble just binaries on your Linux machine or your Mac or whatever, and probably Windows as well. I don't know too much about Windows, if I'm honest, but I think also on Windows, if you just look, there will be some like piece of code somewhere that's basically called start or something like that, which is going to kind of set stuff up in your program. It's going to get the stack in the right way, and it's going to set a few flags here and there, and then it's going to jump to main, and that's like what you write in C. And so what I actually have here is I've got this bootloader.s, and .s is like the, you know, the RISC-V. It's not the RISC-V, it's like the general assembly instruction file extension. Basically, all it does is it says to like the linker, like this is the start symbol, and make a start label. I don't even know if that's necessary actually. Like I know that you need this, but I don't know about this. Actually, maybe, yeah, we're defining the label and then like putting it in the global space so everything sees it. We set the stack pointer to this number, and you'll notice I'm doing the same trick I described here earlier. Like this number is like one more than this. So what we've got here is 2033F, 203FF, and this is now 20400. So it's +1. And then this FFC on the end, well, that's actually -4 in 12-bit encoding. So when you add those two things together after all the extension is done, you end up with the right value of the stack pointer. And then we jump to the main program, and that's the bootloader. That is going to get like linked in with all of the main programs. So then we've got the main stuff, and yeah, so that's what we have basically. And now let's just I promise I'll deconstruct that piece of C, but first let's just go back here because I want to observe something. We already saw that registers here don't have the same names that we expect. Like the stuff that we've been seeing so far in the spec has been like X0, X1, and actually from X0 up until X31, like 32 just registers, and only the X0 has like a very special meaning in the processor, right? That is the only one that has an actual meaning in the processor. But it's not, because there's something called the ABI. And the ABI is the application binary interface. And it's like API, right? An API defines an interface that two programs can basically use to share information with each other. So it can be applied more generally, right? Because you also have things like HTTP APIs and that kind of stuff. But basically what you have is someone defines an interface, like this is how you can talk to me. If you say these things to me, I will say these things back to you. Or I will say things of this shape. And if you give me things of this shape, I'll give you these. That's an interface. That allows two things to come together. And it's the same with the application binary interface. Like we've got a processor and we've got a compiler, and these two things kind of need to play together in some way. And the way in which that is done is the compiler can actually generate much better code if it says, how about, well, it's not just the compiler, right? Everyone agrees upon this. How about we actually make some of these registers have a specific meaning? How about we, we do something like that. So let's actually zip back over to the spec and go down to this page 109, which is the chapter 20 RISC-V assembly programs handbook. And this gives us a nice table. And what it shows us is that for a bunch of these registers that just have these names we're used to have these registers that we're used to seeing in the rest of the document, it tells us what they're called in the ABI terms, and that's what we can use in the assembly language. But it's just sort of this is what the agreement is, as it were. So the X0 register is the 0 register. It's hardwired 0, right? That's the one we've done. X1 is the return address register, right? And that gets set by the caller. So before we go into a function, we put the return address into X1. And that's encoded in the instruction. That is what we did. We didn't explicitly do this, right? We didn't have to do this. And also, this is an interface. You don't have to follow the interface, right? But what this allows for is, you know, the compiler is going to generate jump instructions where the return address, like the RD register is X1. It's always going to use X1 because that's the return address. And if we don't care about the return address, it will use 0. So likewise, we have some more special registers: stack pointer, global pointer, thread pointer, all of these things. We have some temporary, some save registers, plus the frame pointer. So S0 is actually the frame pointer of the stack frame, and we'll see that. S1, we have these A0 to A7 relate to the function specifically, so it's arguments, return values. So A0 is usually where the return value is going. And then we have saved registers and temporaries, and that's kind of how they get distributed, right? And there's no, like, even the compiler will generate code that breaks these rules if it knows it can, right? If it knows that it can get away with like using a register for something else, then it will happily do it, right? There's no concrete thing going on there. So that's what we've got. So let's take zip back over to these assembly instructions and just take a look here and realize, like, okay, we know load upper immediate. That was one we did in the last episode. We know add upper immediate. This J here, that was mentioned earlier as being a pseudo instruction, right? And it's a pseudo instruction that uses the JAL instruction. So that is not a real assembly instruction. Likewise, if we kind of look through this assembly here, a couple of the instructions here are going to jump out as like things that we don't have, and they're also pseudo instructions. So LI, which is a load immediate, that's also a pseudo instruction. Here you can see that what we're actually doing is loading 42, which is, you know, the return value of this function. We're loading it into A5. Then we're doing a move from A5 to A0. Kind of weird. Then we're doing LW, which is a real instruction. And then we have return. Return is also a pseudo instruction. It's also just a JAL instruction. Actually, it's a JALR instruction, if I remember correctly. And yeah, what you'll notice is that we have a few of those. We can actually tell the disassembler to only show us real instruction names. The way we do that is we use this M flag, which allows us to pass like specific stuff for RISC-V. And we can say no alias. Is it no alias? No alias, yeah. And when we use no alias, if I'm correct, I guess it's no aliases. Yeah, okay. So now those return instructions have turned into JALRs. Load immediate and move, they've turned into adds. And yeah, so basically what you'll notice at this point is that all these instructions, we have them all, right? All of these things are implemented at this point, as long as the two instructions we just wrote work properly, which we can test very quickly. So we can actually like basically load this binary, not this specific one, but like another file which is built, which is only the bytes. This is an ELF file, so that has more information in it. We can load this into our emulator and just run that instead, right? So that means that we can actually write C programs, compile them, and now run them in the emulator. That's brilliant. I'm really happy with that. We'll go more in depth with that later. Now, just because if I don't do it, and I don't even know if anyone cares, but just so it's clear, I don't want to have anything in this video that's like, sort of like, oh, what's that magic, you know? Because this certainly looks like magic. If you don't know C, that's fine. It's not that hard. It's really not that hard, especially if you start like at the level we're going to use it, which is a pretty low level because we're not going to have standard libraries or anything. So we're basically going to use it as a nicer version of assembly. It's not that hard. So one of the things you can do is you can define macros. So basically what that means is that if you use this define, you can give like just like a name of a value, and then when the compiler runs through this, it will actually physically replace that name with this value. So all these RAM starts, it's not a variable, there's no space in memory here, it's literally just going to assign this value. like it's going to put this to Jillian here. It's going to put it here. Likewise, you can also write macros that look like functions. So that's what this write to is. This one takes an address and a value, and it ends up replacing anything that matches this. So, i.e. this expression, it will replace it with this. So let's just go ahead and kind of do that below here. And we'll just go in and replace all the macros now. So the address becomes this to bjidlabibdib, and this value is this one. And so kind of what we're doing here is some weird C magic stuff. But it's not, right? Let's think about what we want to do here. We want to write this value to this memory address. We can't just do this, right? You can't just sort of do something like that, because this is a number. That's it. It's a number. It doesn't say that this is memory. Like, there's nothing that illustrates that we're talking about memory here. C does have a mechanism for us to do that, though. They're called pointers. And a pointer is just like a type that represents the idea of like kind of like a memory address. So it's like wrapping up this idea of talking to something in memory directly. And what we can do is we can so-called dereference a pointer, and then we can assign stuff to it. And then what we're doing is like we're saying, no, actually take this value, put it at the memory address. That's how pointers work, basically. They're a bit more complicated than that because they actually have types, and types all have different sizes and everything. You have 8-bit integers and 16-bit and 32-bit and stuff like that. You also have things like, you know, you have other types, of course. And what you can think is that if you have a 32-bit integer, or if you have a 32-bit array, for instance, like you can also do things called pointer arithmetic, or you can do something called pointer arithmetic, which is where you take pointers and you treat them as numbers. So you treat their addresses as numbers, and you can add to them. And if you have a 32-bit integer pointer, like you have, which we're dealing with here actually, if you add 1 to it, you don't just add 1 to the memory address, you actually add like 4 bytes, right? Because you're talking about the next 32-bit integer. It's kind of beside the point for now, but I just want to make sure that all of that's clear, none of it's magic. So if we wanted to dereference this, we would do something like this. We would use this star. That basically tries to dereference the thing inside. You don't. It's not a function, right? You don't have to do that. You can do it like this, but I don't know if this would be like valid. It's just gonna. Well, this actually is valid, but what this tells us in this error message is operand of dereference, this star, must be a pointer type, but it has type int, which is true, right? Because this is just an integer. So before we can treat this thing as a memory address, we need to first turn it into a pointer. So we can do that by casting it to a pointer. So the way you cast something is you kind of put the type inside here. So I could cast this to an int, and this would work, and it's going to say, well, this whole thing is still wrong, right? Because we're trying to assign, but this is valid now. Like we've said that's an int. We could also say something like this is an unsigned int, which is 2 different types, right? UN and int, 2 different types. C has these like multiple named like space between types, which I think is insane. But most people, like, you know, you would redefine the name of this type to be something more sensible, like uint 32t. But anyway, so we can make it unsigned int, we could cast it to an int, and of course what we can actually say is like, hey, make this an unsigned int pointer. So now, like what we're saying is like, this is an int, but like we're casting it to an unsigned int pointer. So like we're saying this is a memory address, it's a pointer of type unsigned int. So the thing that goes at that memory address is an unsigned int. And now we can just dereference the whole thing. So we can, not the whole thing, but like this whole expression that we've converted, we can dereference it. And all of a sudden, this is now valid, right? This, what we've done is we've turned this into a memory address, an actual memory address, which has an unsigned inside. We've dereferenced it so we can actually write to that, and then we put this value in. Perfect. But the problem is that if the compiler sees this, it's gonna look at this expression, and it's gonna see that we have kind of written to a random place in memory, and then we've never done anything with it, right? We didn't like read it back, we didn't print it to the screen, we didn't like try and, I don't know, do anything that like we might expect to be an observable side effect with it. And so the compiler will just remove it. It's just going to say this does nothing. It's like, it's basically dead code. I'm going to remove it. So in order to tell the compiler not to do that, because like, you know, we're talking about hardware systems here, right? Obviously in a regular program on your PC, if you just wrote a value to memory and then you never did anything with it, you probably don't want it in your program at the end because it's not doing anything. It's kind of like probably an error that you've made. But on hardware, especially in embedded stuff, writing to memory can mean other things, right? You're not necessarily writing an address in memory. You might actually be writing to an address on the address space, but it actually turns LEDs on and off, or it sends stuff down a serial line, or whatever. So you can have kind of side effects just by writing to an address. And the way in which we tell C to like understand that there could be side effects to what we're doing is we use this volatile keyword. So volatile unsigned int. So now what we've told it is we've got a pointer to some place in memory, and hey, there's probably also some side effects involved in this. And then that is now enough. And obviously that is a tricky piece of code to look at. So we don't like generally do that. We make a macro, we hide the complexity away, and then we can just make it look like it's a function. We could also just make it a function, but there's no reason to make it a whole function. So that's that. I really hope that was clear. I'm not like the world's best C programmer or something, so you know, maybe I didn't explain it in the best way, but that's the general idea here, and that's how we're using it. Like we're gonna need to make use of this kind of stuff because we're gonna want to like literally turn LEDs on and off and that kind of stuff. So this program is already built, and I've got this build script, and what it does is it just calls the compiler GCC with this linker script. I won't even show that because I've just like yoinked it from someone else, and probably what I should do is actually write my own and not just like take someone else's and not give them credit. So I'm not going to show it on screen right now. But we've got no standard lib, so we're telling it like don't compile the standard libraries, or don't add anything and don't assume that anything is here. Passing the bootloader assembly stuff, so those 3 assembly instructions that, you know, set the stack pointer up and then jump to main. Then we're passing in main, and then we compile and we get this main out. And then that produces an elf file. And an elf is like an executable container that contains loads of information about your program, like more than just the instructions. It contains like symbol information and stuff that can even like link back to the C code. And like, so if you're like running it in a debugger, it's like a source map if you're familiar with those. So there can be loads more information in the elf. And what we want to do is we want to say, we don't need all of that. We just want to get those bytes out. We want to get the pure assembly bytes out that we're going to load into the program ROM. So we can use object copy to basically pull out some binary information from the text section, and the text section contains all the code. So what we do is we feed the binary that we just built, and we get this other file called main.bin. And if I kind of open that up and show it on screen here, you can see a hex dump, and you'll see that the first few bytes that we have are 37, 01, 40, 20, and if we direct our attention back to the assembly that got built here, what you'll see is, well, you need to remember that RISC-V is a little endian encoding, which means we put the lowest part of the number at the highest part of memory, or in this case, I guess like the first address. Like we kind of write it backwards, if that makes sense. I have a video about endian this. So what you can see here is this very first instruction, excuse me, is 37, 0, 1, 40, 20. So that's done that for all of them. And the linker script makes sure everything is properly aligned. So these are the bytes. We're going to load them into the program, and then we're going to run it. And hopefully nothing is wrong. And if it is, we'll try and debug it. I might debug it tomorrow. And of course, that doesn't matter for you. That's it basically. So what we're going to do is coming in here, and we're not going to need these instructions anymore. What we're going to do is, all right, we're going to need to pull in some stuff because we're going to need some stuff from the file system just to read. So let's just import star as fs from fs/promises, promise versions of those, and let's bring in star as path. I actually only need one function from path, but I'll bring everything in because that's the sort of wasteful developer I am. And we're going to make a function here, which I'm just going to call main. I usually do that when I make these like wrapper async functions. Move everything inside that, then run this main function. And now here we can just async await some stuff. So what we can do is we can get the this is going to be like the program, but like a buffer of the program, like a node buffer of the program. So we'll get that by doing fs.readFile. Just do await fs.readFile, and the file we're going to read is path join. We're going to be like so we're going from the dir name, and I think the dir name this is going to assume is the source file, right? So we need to come one back. We need to go into the system code and grab main.bin. And then this is a node buffer. I'm not going to call this. I'm just going to call this file. So dumb. And create a program here. And what we're going to do is we're going to need to take this node buffer and like turn it into a uint32 array. So new uint32 array, and we do that just by providing the file buffer to that. Oh, this is so exciting. I'm like really I'm sure I've made some sort of mistake, so probably going to need to do some debugging, but I'm kind of also just super psyched to see how this works. I tell you what I'm going to do. I'm going to take a terminal. I'm going to put it here on the side. And what I'm going to do with it is I'm going to run the debugger here, but I'm going to put the assembly instructions on the side here. So let's go into the system code and let's just run this command again, the one that I've got in this other terminal that I'm just sneaking out to get. So yeah, what we're going to do is we're going to follow this through, and we're going to watch it execute each instruction and make sure that it's kind of doing what it should be doing, checking it along the way. Oh, it's exciting. Okay, so the debugger is going to catch on the end of every instruction. So on like when it goes past the rightback stage, when it's done with it, we're going to debug, and at that point we know which instruction would have executed, and we can kind of inspect the state as we would expect. One of the things, by the way, one of the things we can do is I I think we can supply numbers. What is this other? I don't remember what this thing is. We'll just have to look back to the spec to get the register numbers. But there is a flag you can pass to get like the actual register names instead of SP, S0 and that kind of stuff. But for the most part, I think we're going to see if this works just by, yeah, that one that just said an unrecognized thing. So we do this. Okay. Enough faffing around. All right, so we executed a load upper immediate to the stack pointer into the stack pointer register of this value. Okay, we know the stack pointer register. If we go back here to the ABI, the stack pointer is x2. So let's have a little look-see into x2. So that's we can do that with this .reg file 2 string 16. Yeah, so I guess it's .value 2 string 16. Is it definitely 2? Go back. It should be x2. All right, let's put a breakpoint down somewhere just to see where this is going wrong. So we're going to decode, and let's just slam a breakpoint down here. It doesn't really matter where we do it, and then we can run again. We should catch here. So is this a load upper immediate? Well, we can look at the next value. It is, so it actually decodes that. That's fine. Let's grab its immediate then. So let's see where it jumps into. So we end up taking the U immediate. So load upper immediate, next value, write the immediate 32. And then if I just look at this dot immediate 32, next value, 2 string 16. That's looking good. That is what we would expect. So let's, I guess, follow this through the registers just to see where it ends up. Actually, which this format 104. Load upper immediate. We end up with a destination register. Okay, yeah, of course. So destination register, what does that end up decoding as? If we look here, this.rd next value is 2. Okay, so yeah, it really should get there. We've decoded the information correctly. So where could this go wrong? It's not going to go wrong in instruction fetch. Memory access. This is the point in which we're going to say our rightback value. So let's throw, this is the one place where I could have messed this up. Since I have touched this part, let's throw a breakpoint here. We end up stopping here. None of those other ones should be true. So we end up saying the rightback value is the immediate 32. Well, that's true. And then in the rightback stage, rightback value valid, it's 1. So reg file rd2 value equals rightback. So then we end up, yeah, so we end up breaking here. So when we do latch next, the register file should latch. But yeah, if we look at that, it actually says next value and value, yeah. I find that really strange. Because we... Oh, 0 should always be... It's kind of a... Yeah, it's kind of a strange thing. Let's restart. I'm probably missing something really obvious here, right? So we get here this .reg file. So we do have a proper copy of the reg file here, right? And we're going to write into it. And so reg file 2. And then here we have these things. So we have next value 0. We didn't end up writing into this properly. Rightback value is, yeah, so what's going on there? So okay, I'm going to place a breakpoint in the register file. Wouldn't have expected to do this. I mean, maybe I messed something up here, but right, so we'll do this. So this is not the point yet. End up setting a bunch of yeah, the tricky part about that, of course, is that we're using registers for everything. So let's just debug, get to that point where we're going to write the register. Then we can put the breakpoint down. So we get here, and we're setting 0. That's so weird. Wait, let's take that out. Here, rightback value. Wait, what's going on? The rightback value is wrong. Okay, that's at least nicely identifying the problem. So what's going on here? Rightback value does value PC plus 4. Is PC, what is PC plus 4 in this instance? Narrowing in on the problem here. Let's have a look. No, that's right. So what's going on here, right? We write the rightback value. Oh wait, PC plus 4, that doesn't make sense. Immediate 32. Oh, and I've already jumped over it. What is immediate 32? 0. Okay, so somehow we've lost immediate 32 along the way. So immediate 32 is decoded immediate 32. So at this point, do we not have it? Immediate 32. Are we not latching it? It doesn't look like we are. There is your problem. I've had numerous comments in the last couple of days telling me I should implement unit tests, and I absolutely should. Okay, at the very least, that looks good at this point. So let's take the breakpoints out. Let's take that one out as well. Rightback value is the right value. And let's read register 2. That looks good. Alright, okay, problem 1 solved and instruction 1 executed correctly. Good, because that's just the one that we wrote in the last episode. Hopefully that hasn't broken since then. Only a little bit. Right, then we're going to execute an add immediate, and we're going to expect that at the end of this that our stack pointer equals this. So same thing, look at the same register, and that is perfect. That's ideal. Okay, so our next instruction is a jump and link. Just basically a go-to, right? We're not storing the return address here. We're just jumping to here. So this should bring us to here, and then we should be able to look at the instruction fetch stage. So this.if.get instruction values out. pc.toString 16 1008. Okay, right, so wait. That doesn't seem quite right then, because we finished executing this instruction. Oh yeah, no, the PC is not going to get set until we actually enter the instruction fetch again. So I think if we were to actually run the next instruction, I'm trying to think, could we have observed this in some way? But since we don't write a return address or anything, we would see that. What we should see is in the next instruction, we should do an add immediate, and we should take 32 from that immediate of the stack pointer. So that's the stack pointer. And if we were to do something like this, right? So stack pointer take away 32, we would expect to end up here. Hopefully that all works correctly. And although that's going to end up getting sign extended and everything, so maybe this isn't going to work out precisely how I think it is. But anyway, we should execute an add instruction. So I've done that now, and I want to take another look at the PC. Yes, that's it. That is where we should be. And what's the stack pointer now? That is the value. Yeah. All right. We're on the way. We actually used the jump and link, so we're at this point. So at this point, we're just doing some stack stuff, right? We're also storing the return address. Like this is all stack-based things, like stack-based stuff. And you'll notice, right, that we're we're storing like wherever we've come from. So we're storing like the return address. And it's funny because I think because I've compiled this program without like a lot of optimization level on, it hasn't realized, for instance, that like this is the main function, and therefore like we don't really have a return address to go back to, which is fine. We're just going to end up storing some stuff at the stack pointer plus 28. We're storing the return address. It's going to be 0, so it's not going to have an observable effect. Then we're going to store S0. S0 is going to contain the... S0 might be a register that we need to set, by the way, because that's the frame pointer. And we haven't set the frame pointer up here, but maybe we don't need to because it's the first stack frame. I don't know. Might want to think about doing that. So we're doing that. We're storing what is a S0 to the stack pointer plus 24. And now, so what is the program counter now? 140, yeah, so we did this one. And the next one should be an add. Adding to S0, the stack pointer plus 32, so that should be observable. So let's take a look in the spec. S0, scroll down a few pages, we will get to the ABI. S0 is X8. So let's observe register x8. I'm thinking, did we execute that or didn't we? Where are we? On 44. So no, actually, I need to do one more. Now we just executed that instruction, so yeah, okay, good. So actually this all works out because this is actually basically saying that like this is where we came from basically. So that's all good, that's all worked out. And the next thing we're going to do is jump into this other subroutine, and we are actually going to store the return address here. So what we would expect the return address of this to be is this, like 10 blah 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 50, because this is like this current address plus 4. So let's actually execute this, which is going to jump us into this function, which we'll start following through. And let's take a look at the return address, which I believe was x1, right? x1 return address. So take a peek. Absolutely perfect. So we're now here. We're doing more stack stuff, right? We're doing stack setup. So I'm just going to skip through these 3 instructions. 1, 2, 3. Now we are here, presumably. So we executed this one, and this one. Should be on this one because we're going to get the next PC on this one. So we're going to load into A5 our return address. Let's take a look in A5. A5, by the way, is so A2 is 12, so it's A15. X15 rather. Boom, that's the number. Then we're going to execute this, which is going to be another load upper immediate to A4 this time. And this is what we talked about earlier with how this addition stuff is all going to work out. So we end up putting that 1 there instead of a 0, which is like the number we're trying to load up, remember? Could even bring up the C at this point, but we can see that this is the number we're going for. It helpfully gives us that. This is a comment, by the way, so all this stuff with a hash is like the disassembler giving us useful information as we run the program. Okay, so we ended up doing this, and then we're going to do this add immediate, and we're going to add A4 with this minus 256, which is FF0. I'm going to sign extend all of that, and then put the result back in A4. The final result should be this. So when we run that again and take a look in the same register, we see, yes, the number we are expecting, which is so perfect. The next after that is actually storing that value. We want to store the value in A4 at A5 plus 0. And so it's telling us it's there. So if we execute this, now we can actually look at RAM. So this.bus.read that looks promising. That's the value. We took the value and we added it and we stored it back in from C. So cool. Oh, it's so great to watch the little emulator grow up. I was so happy with this. Okay, this is great. And then we're going to put into A5. Notice we don't care about A5. We are overwriting A5 now. That had the address before. We don't need that anymore. We can use A5. So we are going to overwrite that. And in A5, we are going to find 2A, which is 42, right? And we're putting that in there, right? We're not adding, so the target is A5, we're adding 0 to A4 to 42. Notice that add immediate is just like a super simple load immediate. And load immediate, that's a pseudo instruction. And we didn't talk too much about pseudo instructions. There's a big table of pseudo instructions in the RISC-V document, which is kind of hard to read because it doesn't properly align table cells, which is like, I have so many good things to say about the RISC-V manual and the RISC-V spec, but I just want to show you this, right? Okay, this instruction, and you can get this from just like sliding your mouse around, but this instruction, LARD symbol, which is load address, like, is it just those two instructions, or does it also include that one? Like, it's not super clear. Turns out it's just those two, and then this next one is those two, and then this one is then those. Like, it's kind of like this one is these 3 instructions, I think. I'm not even sure. Like, it's just like, this is not like, I don't understand why they chose to format this table like this. My one complaint, and I don't deserve to complain, I completely admit that, but that would be my one complaint about the spec. So minor. Okay, so at this point we have loaded up our 42. Now we're going to load, what we're going to do is we're going to basically put, like, copy that to register A0, which is the return address. I don't know why it did this, right? I was looking at this assembly output earlier, and I'm not really sure why the compiler first decided to use A5 instead of just using A0 from the beginning, because it doesn't look like it never uses A5, it only ever copies it, so it just seems that we're just like using some, you know, unused instruction. Compilers are usually really good at that kind of stuff, and I'm pretty sure if I had full optimization mode on, it wouldn't have put that instruction in there. It's just kind of funny. Wouldn't have expected it, but yeah, so we end up doing a useless instruction and writing into A0, which should be 10. Yeah, right, so now 42 is in 10, which is A0. Then we just do the inverse of what we did up here, so we end up storing you know, this like S0 at this address. Now we're basically popping that from the stack, putting it back in S0. S0 again was S0 was X8, so I'm not even sure if there was a value in there in the first place. Oh yeah, of course, yeah. We do that, then we add to the stack pointer, and then we're jumping back to our return address. So if all goes well, like our return address, which was X1, if all goes well with this, we should be back in main, and we should be at this point, I believe. And I'm just thinking at this point, now this is completely my fault. This is a slightly different binary to the one that we saw in the C program. I wanted to, I'll show you the binary that I actually built. This is really stupid. I should have just run the build command again. This C program, which you can see here, it does this, right? But it doesn't do anything with the value. So what I had was just this, right? I had something like this. Int result equals, and then I was like doing like a write to, and it was the RAM address plus 4, and then I was storing result plus 1, because I just wanted to see, you know, the compiler's output for something like this. So this is the program now that got compiled. I do apologize. It's kind of stupid to all of a sudden bait and switch a different binary in to the one I showed you earlier. But this is what we're going to work with, because I definitely didn't prepare that well enough. But what happens is we should be back here. We should be on this address. And when we execute this, what we should be doing is storing the value that, wait, does this make sense? Because now we're trying to store, oh yeah, okay, we're pushing this to the stack basically. So that's just the S0 was this one, right? I think. Sorry that I have to go back to the thing so often. Yes. So this this thing -20 it looks like. So store the thing which is at A0, so our return value at S0 -20. So -20 there. That's the address we're going to look at. And we're going to look at, I said that this was an int, which is a 32-bit value. So when we execute this, I just want to grab the instruction pointer 38. That's actually not right. That's actually not correct. That's not correct by any means. I think this is where might be where I've messed up, because what you can see is in the beginning of this, so here before we call, we end up yeah, S0. I think the problem is that when we end up jumping back, we have the return address now, but this should be fine. I think maybe JLR is not correct. This is interesting though. I mean, I'm really happy with how this works up until this point. This is great. My guess is that there's something maybe wrong here, because the return address, we looked at it before. I mean, it should still be there, right? So return address x1, like this is our return address, and we're jumping to an address which is like that plus 0. So when we got to this point, oh wait, 38. Of course, it's still here, so it never executed that. No problems. Crisis averted. Let's just run one more. Now let's look at the thing. Now we're at 3C. Is that good? 3C. We're back in main. We're just in main. So that's not right. Okay, so there is something's up. Okay, so what I'm going to do at this point is, well, I'm going to rebuild this binary. I'm going to run the build script, and then if we do this again, what we're going to see is slightly different program. Oh no, because did I save the C program with that in it? Yeah. Yeah, okay, so that's fine. Alright, so now we actually have an accurate program. So nothing changed there, of course, because that was the program I had before. What I want to do, right, is that when we get to this instruction, I want to put a breakpoint down. So the simple way of doing that which it would be nice to have a sort of more declarative way of doing this, but what I'm going to do is basically come into the instruction fetch stage, and then at any moment, like if this.pc.next value is equal to it's all squished up, but which address was it? JLOR, this one. Copying this out would have just been more straightforward. Alright, so I think we can just do this. So let's run the debugger again. Hey, we hit. So from here on out, we should be executing this instruction. So I guess I want to see if it's decoding properly. So let's go into decode. Let's not do it over there. And let's just jam a breakpoint. It doesn't really matter where we do it. I mean, we need to calculate the branch address properly. I mean, look, something could have gone wrong here for sure. We'll do it here. Do they use IME? Yep. Okay, so here we should know that this is a JALR. Yes. All right, cool. So we got our immediate. The immediate should be 0. The PC. Wait, is this how it should work? Yeah, it should be relative to the. Does this even make sense? This doesn't make sense. Like, we're adding it to the PC here. And actually, let's take a look at the spec, because maybe I've just misinterpreted this, which is probably it. Oh, of course, yeah. We have a base register. We're not using the PC at this point. We're offsetting relative to a base address. So we don't use PC. We use, what is it, RS1? It's RS1. We have RS1 by this point. It's just RS1 dot next value. So it would just be this dot RS1 dot next value. All right, simple bug. Quite happy with it. Happy with the fix. I mean, I'm not really happy with the bug in general. Let's hey, all right. So we're back here. Let's go back to this. All right. So at this point, I'm running that instruction because that was this, and then that should mean that we're here. Okay. So let's just do a quick calculation. So where are we? It's going to say we're at the old place because we haven't got that new value yet. I guess the way we could look at this is just to look at the branch address, but it's not really worth doing that now. So if we look into register A0, which is 10, we've got our 42 value there. We end up storing that at S0. So S0 was 8 and minus 20. So yeah, like this address, yeah, it's all good, right? I think so. We're going to store that. So just going to execute that statement. Take a look at the PC. .3c. We're back in main. So what's going on here? I know what's going on. and apologies to you if you also know what's going on, because it's probably, as always, quite frustrating to watch. What's going on is that, yeah, to tell if a branch address is valid, we need to do more than this. I even said this at the time, right? So let's just do this. And this is one more reason why we should actually just export isJump rather than decoded is going to be getting these values. And we want to return that. Great. Cool. All right. It's fine. Let's try again. So each time I'm like, oh, I should have counted how many instructions it was to get to that point. Doesn't matter, because we get here, execute the jump. So now we are here. We saw those values before. I'm going to print it back on the screen again so that its reference is there. And let's execute it. Let's see the program counter. That's better. And let's check that address. Let's make sure that we ended up writing that value there. So this.bus.read, and we want to read at the address. So good, so good. Right. Then we end up loading incredible stuff, compiler. Like this is bad code gen. I really don't want to be the person that's like pointing a finger in anyone's face, being like, "Oh, this is bad," you know. But this is, you know, not the best code generated. So we stored the value that we had in A0 into that memory address. Then we immediately load from that memory address into A5. Fine. We don't need to do that, but fine. Then we're going to add 1 to that, and we're going to store it back in 4. Why not? So let's do that. Let's first load it back and then add 1. Now we can take a look into A4. We can see that we get 17. 17? That's not what I would have expected. Wait, have I not executed the instruction that I think I have? So I'm expecting to read the program counter as 58 at this point. Yeah. So what does A5 have in it? Oh, I'm doing like minus 20. 2B, okay, 2B, 43. So that's correct. Then we end up loading this number into A5. So A5 is now going to contain that. Then we add 4 to it. So A5 should now contain like our address, which it does. Then we end up adding, we end up storing that into the address in A4, which this is the address in we end up storing the value in A4, which will be our 43, to the address at A5. So let's run that. Let's check in with that. Where's the bus? 20000004 43. Perfect. And then the instruction after that is just constantly jumping back to itself. So we end up in an infinite loop. So we can look at the address 68. We're just here, and no matter how many times we execute, it should just stay there because we're in an infinite loop. I can't tell you how happy I am that this works. That's really, really awesome. So, like, kind of the conclusion of this whole thing is, at this point, and I actually didn't think we would get here in this episode, but I kind of just got so excited by the prospect of trying it out that we did. We've implemented unconditional jumps. And with that, we have, let's go to the spec just so we can do the highlight. 104. We now have this. We still need to do this this instruction, but it's simple. We have these. We don't have these branches yet. They're going to be the next thing we tackle, and it's going to end up being, you know, not that different from what we've done, only having to check a condition before we actually say whether something is a valid branch or not. And for the rest, we've done everything up until here, and we're just going to be left with these few things at the end. So yeah, I'm so happy that we can run C, or like basically write code in C, and we've got a tool chain to push that through, get the bytes out, shove them into the emulator, and of course later to shove them into the actual CPU, and to be able to follow it through and get a result like that. So yeah, couldn't be happier. I want to thank you for watching along, and yeah, as always, feel free to leave a comment below. Thanks for watching. I'll see you next time.